I cannot see my own slides in the in Zoom. Are you seeing the vault that we built many moons ago in Rotterdam, the black and white slide?
Yes. Yeah.
Oh, perfect. Okay. Well, great. Thanks for the kind introduction. So today I want to discuss sort of the early days of COMPAS and have an sort of an industrial outlook on the projects. So while pursuing my PhD thesis at Hyperbody Research Group, I invited Sylvan Österle and the late Matthias Riepman, author of Rhinovolt, to participate in the project. Rhinovolt is a structural form finding software that Matthias developed while developing his thesis at the Block Research Group, and I kind of consider it a precursor of COMPAS. So there was such a substantial software development that Tom and Philip probably have a far more detailed perspective on it. But let's say that the ties go way back. Here you see the joint faces of the voussoirs that make up the thrust vectors, and yeah, Rhinovolt was a seminal moment, I think, in the development of architectural design softwares, and I think at the time, and this is almost 10, 12 years ago, there were certain overlaps in my own research interests with those of the Block Research Group, and we were working very much on voussoirs, on the stereotomy, and in a sense, this work was pleasantly equivocal, rooted in many centuries of architectural tradition of stereotomy, while empowered with custom CAD software, right? So I think that really speaks to the earlier presentations of today, is that COMPAS is not only a software engineering effort, it's very much feels like a cultural effort as well. And it's actually kind of interesting is that those efforts aren't disjoints, right? Is that they beautifully flow from the software engineering domain into the cultural one. Interestingly enough, that theme of working with natural materials continued to develop, also by the work of Maragio Barbero and the New Fundamentals group. But the most seminal project of the time was for surely the Armadillo Vault. And another interesting overlap, I think, is that both Matthias and myself were very much working on segmentation of surfaces or discretization of designs, and bringing these to designs that could be fabricated, and considering the fabrication integral part of the design of a project. So this is kind of a famous image, a 19th century idea of how architects would work by the year 2000. So who knows, we might have chipped in. But specifically, I want to focus on how the development of Python OCC has informed also these architectural projects, and that these distinctions between software engineering and cultural engineering, the production of culture, are sometimes a little bit blurry, these distinctions. So briefly, I go back to this slide of how Matthias worked on the discretization of the Armadillo Vault, and I want to bring this to your attention. Is that so? For almost 18 years, I've been involved in the Python OCC project, and it's pretty interesting in um, how let's say software, the building of software led to novel method of surface segmentation. So I want to take you through the process just a little bit. So on the top left image A, you see a Rhino surface. That surface was exported as a step file and this step file was read into by Python OCC. With Python OCC, we calculated the Danielson distance field. And what was pretty unique in the project is that actually the surface segmentation was fully executed in image space. So after this from B to C is a process of discretization. Excuse me. On C, you see the distance field. On D, for instance, you see the curvature sampling, and it becomes pretty interesting when we see the image E. Well, here you see two images superimposed, right? So these are basically pixels for your understanding. And one aspect is dealing with distance, right? So for instance, if we're hot wire cutting a structure, you know, the length of the snare of the hot wire cutter only is limited of size, so you need to discretize it. But in a sense, you want to distribute form there where it occurs, right? So that's what you see in image F, right? In the red area, you see that lots of segments occur, right? So form is distributed in a manner of scarcity, I would say, right? Is that focus there where there's lots of curvature, basically. So I think this was retroactively kind of ingenious. Because without tools like Python OCC, it would have been impossible to like cross these domains between image analysis, the use of level sets as provided by toolkits as ITK. So there, yeah, that was something of a breakthrough, and that research work was also built into a pavilion. You sort of see the medial axis. Sorry, I'm going a little bit too fast here. In the right-hand side image, the yellow contour is actually the medial axis, right? So the maximum distance between the border of the surface, and actually in its physical manifestation, you also can see back that medial skeleton. So that brought us back to the history of voussoirs. Recently, I visited the city hall in Arles, built by Jules Hourdin in 1668, actually. And Hourdin inherited Mansart's collection of drawings. And actually, Mansart is of the famous Mansart roof, right? And I want to draw back to that cultural effort of software engineering. Tom earlier today presented the CGL library, where you know this is actually the straight skeleton algorithm in CGL, which is the essential Mansart algorithm, I would say. So this tectonic infatuation has continued also in my work, in my research work in concrete printing, and continues to this day, this fascination by surface segmentation in my work in earthen construction. Interesting. last year we won a major tender to construct a next generation acoustic barrier, where we won the tender from other very large construction companies in the Netherlands. And next year we'll build 125 meter of acoustic barrier. And actually that theme of acoustics was introduced to us by the Grammatio Köhler group, specifically through collaboration with Actual and Romana Rust and Matthias. So that was sort of my reintroduction, where Rhinovolt and the work with Matthias felt like a first introduction of a precursor of COMPAS. So COMPAS was sort of reintroduced in my time as technical director at Actual. And let's say I have a difficult relation with Grasshopper. I'm not exactly a fan of it. And when I saw how Romana utilized, how she wove COMPAS and Grasshopper together, I had to sort of reassess my beliefs, because it was very elegantly and very efficient how things were developed. So I come back to Python OCC over and over again, since it was what the ambition is of COMPAS is my own software ambitions were of a similar kind of scope and magnitude. So it's also been really rewarding to see Python OCC included in woven into the fabric of COMPAS. And again, what is interesting is that Python OCC allowed for new avenues to be explored. I aforementioned this in surface segmentation, but also into it provided also the underpinnings for my first startup, Odico, which centered around hotwire cutting. And since hotwire cutting is really fast, there was a need to develop software that compiles motion planned robotic tool paths in a highly automated fashion. And all of that software was developed on top of Python OCC. And it was, yeah, I surely missed a library such as COMPAS in those days. Absolutely, would have made life substantially more pleasurable. But in a sense, what I want to point out is that the realizations such as well, with Odico, we made a commercial breakthrough with the Fjordnews project for Oliver Eliassen, which required over 4,500 square meters of hot wire cut formwork. And that simply wouldn't have been possible without the software engineering tools, right? So the link between the tools is that, and in software engineering, people refer to the word building all too often, right? And in our domain, I think software building and building is so strongly correlated that is yeah, just something incredibly fascinating. Gonzalo made a very generous invitation to come up with some provocative ideas and comments on the development of COMPAS in our sphere in general. But well, let me start by expressing how excited I am to see that the YAG integration also, which makes the 5-minute experience of COMPAS so much more welcoming, I would say, is that some of the thresholds in working with COMPAS will be eradicated, I think, through that effort. And it reminds me also of So what I want to draw some parallels between the development of Python OCC, which has been a reasonably successful open source software, and across COMPAS. To install a package like Open Cascade is incredibly involved and complex. And a lot of the libraries actually were built in the 90s, right? And required Silicon Graphics workstations and incredibly involved licensing schemes. And is that those were also the underpinnings of the architecture of Frank Gehry, right? And what is fascinating through tools like Condas, these softwares can be installed within 5 minutes without um, having to pay up a considerable licensing fee. A motivation for us to develop Python OCC was also that we did quite a bit of work in working with CATIA in those days, and we got a not so friendly call from the attorneys of Dassault suggesting either to give up the work or purchase a plugin license software development kit for an absurd amount of money. So these tools are available to us today. And I think the sphere of CAE software is at a very interesting point. For instance, tools like FreeCAD, you see that commercial development is starting to take place, and that open source software development within the field of construction architecture and engineering is really a maturing domain. I want to point out, are some of you aware of this open letter that was sent out to Autodesk while the COVID crisis was ongoing? And basically it was, the top officers in London complaining about Revit. But I also want to remind you that Gary and his office developed a kind of parallel of CATIA specifically for the CAE in the industry. So I think those are very important indications that our industry is ripe for revolution. And a very illuminating moment for me was to see the parallels between STEP and IFC. For instance, this is a very, very simple description of a cube, a basic block in IFC as a STEP file. And this is the IFC version. And so basically you see that IFC is prefixed and the underscores are gone, but basically there's not STEP and IFC are incredibly closely related. So here, for instance, in this slide, you see the very modest differences between STEP and IFC files. And the reason for mentioning this is that, well, we should consider IFC the lingua franca of our industry. And there's basically one Python module that will allow you to read and write with these files, which are a gorgeous part of the COMPAS environment. So what's interesting is that early ambitions of the Python OCC library have come to fruition over time. For instance, the machine learning of Autodesk is being built on top of the Python OCC library, which I find absolutely mind-blowing. But also what is mind-blowing is that to properly work with IFC files from the dominant IFC software Revit, it requires a crutch like these open source packages to get the data conversion going. And that's super ironic because mind you also that Autodesk was the large industrial partner that initiated IFC, while now, let's say, support for their own standard has now fallen to such a low degree is that people are taking, writing plugins to parse IFC files. So I hope it's all right if I discuss some of the aspects, some of the challenges involved in developing COMPAS, which are tied. It's quite difficult to explain why it's quite complex to do so. And Tom earlier spoke about how support for Rhino is essential from the COMPAS environment, and I want to elaborate on that a little bit. So traditionally, in a sense, as a Python developer, you invoke CPython and you can launch your debugger and interact with your software in a very interactive, and it's very easy to debug essentially. But in a sense, there are so many levels of indirection to so the call stack from invoking Python from Grasshopper in a sense has so many levels of indirection that it feels like this kind of Russian doll situation, right? Where it's really which makes the development and the hardening of these softwares really, really challenging, right? There's no proper debugger support. So I really want to make a call out for how can we perform unit testing across Rhino, across Grasshopper, which is quite challenging also in terms of licensing, and it becomes really hard to run examples as unit test. And a major learning from the development of Python OCC is that the project advanced quite a bit when we littered the examples code with assertion statements, right? And I think sometimes the first 5 minute experience with COMPAS is a little bit hindered, since it's really difficult to perform unit testing in domains like Rhino and Grasshopper, and that probably requires a little bit of extra love. So also a shout out to the COMPAS Timber developers who are doing incredible work, and yeah, I think that work is really exemplary in how tools like Grasshopper can be supported in Python, and just the elegance of their structures. And well, I reference to the COMPAS Timber code from time to time for our own developments, right? And it cures sort of Grasshopper from these graphs of hundreds and hundreds of nodes and makes it compact and elegant. And still, that resolves my main issue, I think a considerable drawback of Grasshopper, with this incredibly involved call stack, right? You can still run your unit tests in as native Python code and still reap the benefits of the considerable effort of the Grasshopper ecosystem. So I think speaking for myself, is that one of the major benefits of COMPAS is important conventions that the project implies. And I want to call out, for instance, the backend features in COMPAS Fab. So it's very easy to integrate your own collision detection, IK solvers in the COMPAS Fab stack, since there's a structure that you can inherit and just weave in a couple of calls and really advance, let's say, the state of your the of your robotic fabrication with minimal effort. And those conventions, I think, are incredibly important, right? This is a software architecture that can be inherited and extended. And I think it's a triumph of software engineering. So this is wonderful work. So big compliment to Gonzalo. And also something that we didn't achieve as Python OCC is that, I mean, this is a behemoth of a cat kernel. This is over 20 million lines of C++ code, right? And somehow Tom and COMPAS OCC has sort of boiled it down to just a couple of lines which allow you to read in step files and which is just mind-blowing, just incredible. I'm gonna fast forward to, I'm a bit jealous actually of the Blender guys, right? Is that over time, and also being a bit of a 90s child, right? Sort of Maya was a significant piece of software in the 90s, and an important reference, for instance, the architecture of Gremlin of Lars Spijbroek was built on that. And Blender as an open source software has really overtaken the quality of Maya. And it's an exemplary open source software. So the reason why I'm so frustrated is that, and why I think we all should be want to share that and imply that, instill that frustration on you, is that, you know, um, the digital content creation has an incredible software architecture, an incredible environment with ecosystem with Blender. But our industry is, so the industry of CAE software is 10x that of the DCC, of the digital content creation. So why on earth is it possible that that is not reflected in the state of the art in terms of software? My point in case is that we should be economically in a much more in a much better, we should be much better positioned to develop open source softwares. And again, I want to refer to a set of slides of that Tom presented earlier. And it's very true that a lot of the ingredients exist and are already there and are available in Python, which is absolutely wonderful. So it's important to think of this in topological terms. These are the vertices. The vertices are strung together by edges and are formed together, are strung together in an environment such as COMPAS. But moving forward and continuing to build on that will lead to a software environment that I think will be unrivaled to the conventional softwares. So not only has COMPAS incredible momentum, but I think also culturally the time is ripe and up for the taking. All right, thanks for your attention.